Hello, today I will be presenting our work on robot communications. We talk about the interaction between the robots, especially the mobile robot. The challenge is to deal with its position and the wireless communication delay while interacting with other devices. So, the title of my talk is Low Latency Peer-to-Peer Robot Wireless Communication with the Edge Computing. We are going to start talking about our important components in the smart factory, which are the mobile robot, the edge computing, and the wireless communication. And then we'll explain our problem statement and our methodologies. After that, we'll go through our experimental results at last. So let's get started. First, I'm going to specify on the mobile robot, which plays an important role to the smart factory. Why? Because of its services and flexibility. It can carry things and go everywhere inside the factory conveniently. Due to the flexibility, it is wireless, and moreover, edge computing and low latency communication are needed to increase all the machine performance. So, how it affects the whole system? Considering our scene, mobile robot is coming to receive the package from the manipulator, and they must follow the same trajectory at the same time during the drop-offs. The trajectory of the mobile robot is programmed to follow a planned path from the edge computer, shown in the green line, whereas the manipulated trajectory, the blue lines, is assumed to be precisely controlled and can be changed on the fly. However, due to the non-ideal environment, the actual trajectory of the mobile robot could be different, shown in red. So the mobile robot must know its current position and send this actual position data to the manipulator joint controller, which means the blue line need an adjustment to track the red line, not the green one. If the mobile robot frequently tells the manipulator, the correction of its movement would be more precise. So this technique is possible only with a wireless network that has high data bandwidth and low latency. In fact, when dealing with the wireless network, the delay of data transmission is concerned. The actual path that is sent to the manipulator is still the correct position, but in the past. So it never knows where the mobile robot is at the present or it will go next. To overcome this issue, the estimation for the future is required, and the best forecast is at the edge computer due to its processing power. To conclude, the low latency wireless communication and the edge computer can issue corrective action to other devices in the system. In this research, we are dealing with two errors, the position error and the time error. We have two approaches to deal with these problems. First is the prediction. We are going to talk about the hardware setup of the mobile robot first. The Raspberry Pi, camera, and the LiDAR sensors are installed on the robot. With the Raspberry Pi, the mobile robot can communicate to other devices wirelessly. And then consider the prediction process. The edge computer generates the trajectory and sends it to the mobile robot. The mobile robot can move along this planned path by its encoder using odometry method. Due to the non-ideal environment, the trajectory error is accumulative along the walk, but it can be corrected with the machine vision or SLAM method. The raw position and timestamp of LiDAR scan are sent to the edge computer, so it can calculate and predict the future of the mobile robot, and then send to the manipulator or update them to the manipulator. The estimation not only tells where but also when the mobile robot will be in the future. Note that if the update rate is high, the adjustment of the manipulator would be more accurate. That's why we need low latency wireless communication or our next approaches. Low latency wireless communication. To achieve low latency communication, all the data will be organized through the Wi-Fi AX. This uses the feature called orthogonal frequency division multiple access (OFDMA) to accommodate more users on the same channel, providing great network capacity, higher efficiency, and low latency communication. All in all, we still need a network architecture to manage this data traffic. Consider our network architecture. We propose a software-defined network approach. The control plane, the dashed line, is a centralized controller handled by the MQTT server, while the data plane, the solid line, consists of data from devices that needs to respond to each other. The key point of our architecture is to minimize the packet size of the data communicating in the data plane. For example, in our case, with this architecture, the mobile robot's data will be sliced into two parts: the identification data, ID, and the actual data, the data A. In the first phase, the identification data is sent via the control plane, MQTT, and then the manipulator will know the mobile robot IP address by subscribing to these topics. So reliable peer-to-peer communication will be created after that at the second phase. Finally, there is only the actual data part left that needs to be streamed using TCP/IP or UDP/IP protocol in the data plane. As you can see, the packet will be more lightweight, so the transmission of data rates improves and the manipulator trajectory adjustment will be more accurate. Well, for the overall, all the data management is going to be like this. After receiving the path from the edge computer, the mobile robot sends its dynamic IP address or ID to the MQTT topic, which the manipulator has already subscribed. Then, connection is created. The actual position and timestamp data from LiDAR sensors or data A is sent to the edge computer to predict the future field's position and the time. The manipulator will receive the actual position and timestamp from LiDAR 2 because it can be compared with the estimate data from the edge computer, so the trajectory of the manipulator would be adjusted more precisely. To keep in mind again, the estimation not only tells where, but also when the mobile robot will be in the future. So, going back to the challenges that we have proposed, these errors will be corrected by the prediction of the edge computer. The position error is solved by the SLAM method, and the time error may seem to be solved by the timestamp too, if there is no communication delay in our system. Our simple future timestamp is the solution to the time error. However, in fact, low latency wireless communication still gives latency, which makes the time prediction more complex. So, while calculating the future timestamp, the delay measurement needs to be added into it. To measure the one-way delay in our method, all the device's clock need to sync with the edge computer clock so they all can have the same time reference. Then, when communicating each other, the measurement is made up by calculating the difference in the time interval between their timestamp. For example, the data is sent with the timestamp 1 and received at the timestamp 2 at the receiver side. So the latency is timestamp 2 minus timestamp 1. For the results, first show the edge computer which generates path and select the recommended path for the mobile robot by using probabilistic roadmap in MATLAB programming. The base path A, B, C, D, E, F is then sent to the mobile robot. And when the mobile robot is roaming from this generated path, it successfully sent its slider scan to the edge computer where SLAM algorithm is executed. Now, the edge computer saw the current position of the mobile robot and imported into the MATLAB map. After import the scan data to the environment, the comparison between the ideal and actual data is exploited. A, B, C, D, E, F is the ideal path. Meanwhile, the others are from LiDARs. So that's how we deal with the position. What about the time? For measuring the delay, our setup of a wireless network would be based on Wi-Fi AX, and the coverage communication protocols are TCP/IP and MQTT protocol. As seen in this slide, we successfully measured the delay from the timestamp prediction. 2,873 bytes of data has been sent with the data rates of 10 Hz for 20 seconds period during the roaming of the mobile robot. It seems that our communication architecture achieves low latency with an average of 1.5 and 1.6 milliseconds. However, the latencies could increase to the maximum of 6.7 and 6.3 milliseconds for the TCP and MQTT protocol respectively. That's all we do in this research. We successfully set up a wireless network architecture which gives low latency and high bandwidth during the operation of the mobile robot. This allows the system to reach high computational performance. The result position of the LiDAR was then used to correct the position of the mobile robot, and the latency measurement method is appropriate enough to compute the time prediction. At last, we hope that our research would have some prospect for the next generation smart factory. Thank you.